Yes, here we are once again. It's the physics video lecture. We have Physics 105A, video lecture 2. And we'll pick up where we left off. I'm going to write down Newton's law again, and we'll continue our discussion. So everything we're going to do is based on Newton's second law here, and more generally Newton's laws of motion. But you've seen this before. Mass times the acceleration equals the net force. So we already talked about just kinematics, and in particular the law of free fall, which led us to understand that we need accelerations. Okay? And to get accelerations, of course, we need position velocity. So we'll be doing quite a bit of kinematics coming up shortly. Then we discussed force and the vector nature of force. So everything here has significance, right? We've got vectors here. These arrows on top of the letters indicate vectors. Force is a vector. I showed you in some static cases with strings and tensions. And what I'm now going to do is bring in the discussion of what the mass means and put some of these things together. Now the demonstration I would show you, or actually it's a lab activity that we often do here. So I'll just draw right here, demonstration, is of two masses that are connected by a string. Got one rolling across a tabletop. So okay, we draw a tabletop, and up on this tabletop we have car, we're going to call M1, and it's connected via a thin string that goes over a little pulley here to a second mass that's hanging here, M2, and you can imagine the system has no friction, and you release this thing and it just accelerates forward. This one moves down at the same time. So that's what we're going to analyze in terms of Newton's laws of motion. And the idea is the argument could be turned around. The analysis of this could actually allow us to learn something, to get this law here. So here's what I'm going to do. You guys have done this before. Free body diagram. We know we have mass times gravity here, and we have M1 gravity here and a normal force. But in this particular situation, there's going to be no friction, so these two cancel each other. Let's go ahead and write here, no friction. The string that's connecting these things is essentially massless. The little pulley here is massless as well. So what we do have is a tension labeled T that's pulling this car forward, and that's being supplied by this tension T here. And the reason I can equate these two tensions is because the string is massless and Newton's third law is in play. So the first thing here, we have no friction. We have Newton's third law. Which is that the forces between these are equal and opposite, so that's why these two are the same. And then we've learned to do a free body diagram and set up Newton's law. So I'm going to go ahead and repeat that. We'll send this up. Okay, so here's what we do. We've already agreed these two are just going to cancel each other out. So for the first car, we have mass 1 times acceleration is equal to tension. That's it. That's Newton's law. For the second car, we have mass 2 times acceleration. And here, for the right side, we can say there's a tension pulling back on it and there's M2G pulling down on it. So we have minus tension plus M2G. So those are the two equations, Newton's law based on that free body diagram. A nice way to work this is that we're going to add the left side and add the right side. So here we get M1 plus M2 times acceleration equals, now t and a minus t goes to 0. We'll see later in the more formal theory, this is a property of internal forces. We could say that's an internal force to this system, they cancel, and so we're just left with M2 times G. Okay, now I'm going to go ahead and solve for the acceleration. It's M2G divided by the sum of the two masses. Okay, so let's put a box around this and discuss it a moment. What you'll notice here, let's go ahead and analyze this. We can compare it to the law up there. Suppose we were to solve for acceleration, we'd have net force divided by mass. Okay, and this is a one body problem, this is two bodies, but very important point, this M2G, this weight here, just the weight that's hanging there, we could say that's the force that's driving that system, but notice that M1 and M2 are there providing inertia. Okay, it would be easy to think differently, okay, because up here this mass is playing a role as a gravitational mass. This one up here is just a purely inertial mass, but they're both the same. So both of these masses are providing the inertia to the system. So if you were using this and experiments along these lines to discover Newton's law, this would be the point where you discover something about inertia. Both of these masses are equally involved in the inertia. Okay, only one of them is involved in the force. So before Newton's law comes around, we don't have the proper concept of inertia. Okay, and you can say this is a way to develop that. So continuing here, I'm just going to put this important note. The mass is inertial. Okay, the inertial mass. Over here, it's the weight, mass times g, so that's the gravitational mass. So it's inertial mass as well as gravitational mass, and you could say this would be the discovery. One could, for example, do a series of experiments where you just stack a bunch of masses on the left and sequentially move them on down over to here, okay? And you'd get an interesting pattern in your acceleration data, and you'd have to analyze those data to discover what this mass is doing. Both of these masses are inertial, only one of them is gravitational. Okay, so mass has inertia. That's a resistance to change of the state of motion. Change of the state of motion, and which would basically be Newton's first law. And like I said, we made use of Newton's third law. So now we have all the ingredients in place. We know about inertia. We have to study kinematics quite a bit. We know about forces, and the combination of these quantities here is a schema for solving all mechanical problems. Okay? That's, that's Newton's law of motion. Okay, so we're going to start taking these ingredients one by one. The first thing we're going to do is start talking about vectors. Vectors and coordinate systems first, then we'll go into the kinematics again. And of course, eventually the entire thing is referred to as dynamics. So let me put that down as some terminology here. So we have kinematics. That's just the study of motion. And the motion that we're talking about, motion of some object. And so there we have position, velocity, acceleration. And differentiation and integration of expressions like this. That's kinematics. Then the term dynamics refers to motion under the influence of forces. Now, kinematics is purely descriptive. There can be forces involved, but mathematically we're just dealing with these quantities right here. So dynamics we can just say forces and motion. And as soon as you do that, of course, the mass is involved. So forces and motion. And like I said, like I just demonstrated, Newton's law shows the mass is always going to play a role. So involving mass. And as we'll see more next semester, mass and its particular distribution. For the time being, we're dealing with what are called point masses, where we just have a little location in space. So, the cap of my pen that I'm holding here, or a tennis ball, or what have you, is just described as a location of a single point in space. Okay, we'll get to that. So for now, we're going to begin with vectors. I'll write Newton's law down one more time. Equals the net force, and what this formula now involves mass, so inertia, vectors and their derivatives, so all of kinematics, forces, vector nature of force, and when I say net force, I mean the vector sum of forces. Okay, so I can add vectors as we saw last time. The net resultant of those vectors would be the net force. So now that we've studied this at this level, we already see how much is embodied in this law right here. Formally, mechanics, especially at the level we're doing it now, is thought of as a branch of mathematics, in fact, in which there are certain axioms and definitions, and one supplies certain types of forces, and then it's a well-defined mathematical problem. So we're not quite that formal, but it's a good idea to keep in mind. Okay, so now we'll begin with vectors. Some of this, or a lot of this, is review, but we'll get some important nomenclatures there. And we'll extend it soon enough. Get some interesting new material. But for starters, let's just look at vectors, probably as we've learned them before. So vectors and vector algebra. So we could start with some quantity actually, important note, the just the fact that vectors add like arrows. I like to actually start this off this way, so put this in a quote. Vectors add like arrows. Because with this little slogan, you can actually invent, reinvent, rediscover, remind yourself of all the laws of vectors. They simply add like arrows, which means that if this is A and this is B, then here I'll do different color. Then C is literally the addition of these arrows here. Okay, so that would be my A plus B equals C. Okay. Arrow addition. Now, if we want to talk about vector axioms, which I want to do now, I just want to give the several definitions in the abstract that allow us to define vectors. So let's call this definitions. So what we have is some mathematical objects with certain laws of addition, subtraction, and so forth. So we're going to say, first of all, or how about zeroth? Say we have a coordinate system. Components, then we could have, let's say, x, y, z. We have some vector A, and we can say A equals ax, ay, az. So I'm starting with a Cartesian system here. So now we'll just talk about these axioms. Equality of vectors, so we could have A equals B when AX equals BX, AY equals BY, AZ equals BZ, so as defined right here. So that's when these two vectors would be equal. Next, and the geometric interpretation's actually already been given. So next we have addition of vectors. So we have A plus B for AX plus BX, AY plus BY, AZ plus BZ. So that will define our addition of vectors. What about subtraction? First, to talk about subtraction, I'm going to write multiplication by a scalar. So then I'm going to multiply, I'll use multiplication by a scalar. Alpha times A would be alpha AX, alpha AY, alpha AZ. And now if I want to talk about subtraction, A minus B, I have A minus B equals A plus negative B, where of course my minus -1 is one of those scalars that I just said I would do. Using alpha A, multiplication by a scalar. We have subtraction. Then we have commutativity, associativity. I see here in my notes I have the null vector, the 0. We don't have to put an arrow over the 0, but 0 is equal to a minus a. And now we can talk about the commutative law and the associative law. Commutativity, a plus b equals b plus a. And then the associative law that you've seen before. And then the distributive law. So good. Associative. That is when you take a plus b plus c and you add these two first and then add to a, and then that is a plus b plus c. So that order of addition doesn't matter either. So you can reverse them, commutative law, associative law. Put them this way, and then finally the distributive law. And that would be referring to the multiplication by a scalar. So alpha times a plus b is equal to alpha a plus alpha b. Okay, so those are just your basic arithmetic laws, but it turns out that with these 8 definitions, you can take any mathematical object, and if it satisfies these 8 conditions, you can call it a vector. So the first thing we could do is extend the definition to objects with more than 3 components, and less than 3 for that matter as well. So anyway, anywhere from 1 to n, so n components. And that's something we're going to become familiar with, because we're going to move up into any, n with any arbitrary integer there. So n components, you could write a sub 1 all the way out to a sub n. So these are possible. And another thing that's possible is to take more complicated objects. For example, instead of these types of objects, which we interpret as arrows, you could take matrices or other more complicated mathematical objects. We'll see later you can take functions, simple functions of a variable, show that they satisfy 1 through 8, and therefore you can treat them as vectors. We'll deal with that later in the semester. But for now, this is all pretty familiar. And I'll just say a couple more things about coordinate systems and scalar and vector products. And then we'll be set up here. We're going to define everything first in the Cartesian coordinate system, and then we'll generalize a bit. So Cartesian coordinate system, that's when we have our 3 perpendicular axes. We can call them x, y, z for the moment. And we place an arrow in this system. Okay. And we want to discuss that a bit on its own. Okay, so we need, first of all, the components. So we have A as before, AX, AY, AZ is an ordered triple. We then want the magnitude magnitude of a vector, we can just take the letter without the arrow on top. Okay. So that's the magnitude, and we just have, since we're in Cartesian coordinates, we just have ax squared plus ay squared plus az squared. So once we have the magnitude of a vector, we can define a unit vector. A unit vector is a vector of length 1 and say we want the unit vector in the direction of the one we already have here, of vector A, then we can, I'll just use the letter n for the moment, unit vector, and I'll call it n sub A. That would be the vector A divided by its magnitude. So that's a unit vector. And now, so we have that, we can take unit coordinate vectors so we can take this coordinate system and we'll construct it out of 3 unit vectors, and then we would call this x1 I hat, the y direction we call j hat, and the z direction we call k hat. You've possibly seen that before. So these are the unit coordinate vectors, and I hat in the ordered triple form is going to be 1, 0, 0. J hat is going to be 0, 1, 0, and k hat is going to be 0, 0, 1. Right? And by all these definitions, they're clearly unit vectors, and we've got the directions of them as well. Okay, so once we have the unit coordinate vectors, we have the definition of a unit vector, we have magnitude, components, we can now write a vector in terms of those unit coordinate vectors. So let's go ahead and write here next. We can write the vector A, which AX, AY, AZ is an ordered triple. We can also now say that is AX, which is a component, times I hat plus AY times J hat plus AZ times K hat, right, in terms of those unit vectors. So we just want to become comfortable seeing this in any of these forms. Okay, so we now have 2 things we have to look at, the scalar and the vector product. And we'll make a little, make a couple interesting assignments out of those. So the scalar product, also referred to as the dot product, takes 2 vectors and assigns a number to them. So we can do the following. We can define it like this. The product of these 2 vectors, that takes 2 vectors and turns them into a number, product is a number, it would be the product of the magnitudes times the cosine of the angle between A and B. On the other hand, or we can write A dot B is equal to ax bx plus ay dy plus az bz. Probably you've seen both of these, but what I'm going to ask for homework is prove this. Prove the equivalence of these two definitions. Of 1 and 2. Okay, I'll name one of these 1 and one of these 2. Okay. And so here's how we're going to start. I'll get this one started for you guys. So this is homework. What you can argue, first of all, is that if you have two vectors, they span a plane. So you can choose a plane in which these, without loss of generality, you can take these two vectors that live in 3 dimensions and you can say, let's just restrict them to an xy plane. So we can do something like this. Okay. No loss of generality because we know that the two vectors only span a plane, right? 2-dimensional space. So let's go ahead and do this. First of all, and then without loss of generality, we can let one of the vectors lie on the x-axis. Okay, why not? It's just what we're doing. Originally, just to point this out, originally we just have two vectors pointing every which way. Okay, two vectors one direction and another direction, but we know they span a plane, and now we're adjusting our coordinate system so one of these vectors, A, is along the x-axis. Like I said, no loss of generality here. So now we're looking at no loss of generality, but of course you have to state what you're doing because, you know, it does look less general. So now suppose we have A here, and now we'll just take another one, B, and there's our angle between the two. Okay, so, you know, half of the problem was setting it up like this, and now you can carefully prove the equivalence of these two definitions. Okay, so that's a nice scalar product example. And another thing to look at while we're at it is this. A dot B is equal to, I'll write the whole thing out, AX I hat plus AY J hat plus AZ K hat dotted into B, the same thing for B, BXI hat plus BY plus BZK hat. Yeah, if you multiply this whole thing out, what are you going to get? 9, 3 times 3 expressions, but then you're going to be looking at the orthogonality, namely the angle between IJ, JK, and KI. Those are all 90-degree angles. Cosine of 90 is 0. Okay. So this thing here, along with that, gives you this expression. Of course, we still want to prove this equivalence there. Good. So good, you're going to prove that. Let's look at the vector product as well. Yeah, there's our scalar product and the basics of it. You want to prove that, we set it up. So the vector product and this is A cross B. It's got a little more complicated formalism. So A cross B, I'm going to define it as, in this determinant formalism, you take your I, J, K hat vectors, more room, and then you have your AX, AY, AZ, BX, BY, BZ. And this is a determinant. And so we want to do a couple of things here. First of all, go ahead and write this out so you know what the components are in terms of I, J, and K hat. So that's the first thing here. And then there's another definition. So this is our first definition. The second part is to get the magnitude. So magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle, sine of the angle between A and B. And that one we also want to prove. That one we also want to prove. And again, you're going to have your definition here. Prove this. And the proof you're actually going to argue the same way. Okay, A cross B, we can set it up like this. Okay, without any loss of generality. Right, you'll have a limited number of objects there. You got A, B, angle between the two of them, and then you want to, use the result from here in a geometric argument, or analytic geometric argument, to prove that the magnitude of that resultant under these simplified conditions, which have no loss of generality, is AB times the sine of the angle between there. And the same discussion holds true for this. Now you could do A cross B and set these up here with the cross product, but then you have to know something about I hat, J hat, and K hat. So in the conditions of the cross product, I, J, and K hat form what's called a right-hand system. So let's go ahead and erase this. So again, important note right here. I hat, J hat, K hat form a right-hand system. And what that means is the cross product. So I hat cross J hat equals K hat. Okay, let's draw our picture here. So we can kind of do some I hat, J hat, K hat. There's a perspective, right? I hat's coming out the board. So I hat cross j hat k hat by the right hand rule. You may have learned it in different ways. Right hand thread rule. So I hat cross j hat is k hat. J hat cross k hat is equal to I hat. And finally, k hat cross I hat is equal to j hat. Okay. So those three cross products, they take a unit vector into unit vector, and the resultant is always perpendicular to the plane spanned by both of those, perpendicular to each vector in the product. Vector product A cross B equals C always defines a right-hand system itself. Okay, C is always perpendicular to A and B, and C is perpendicular to A and perpendicular to B. So yeah, you got a couple proofs just to look at these things. And again, the determinant rule follows from A cross B equals, okay, here's what we'll do, AX I hat plus AY J hat plus AZ K hat cross product. So this time you're going to get all 9 of them, you know. EX I hat plus EY J hat plus BZ K hat. So if you multiply all of these out, you'll get your determinant rule as well. And finally, the only thing I haven't mentioned here, which is part of these definitions actually, is that A cross B is minus B cross A. So you don't have a commutative law. In fact, you reverse the order, you get the negative of the original one. Okay, let's have a look at the clock. Wow. Clock says we're almost done. Okay, well, this is important stuff. So I'm going to have one more problem I think I could find for us to do here. And I think these will all be due on Friday. Let's see here. Maybe the triple product. Yeah, do one more thing. I have this one written out here. Yeah. C. Now this can be shown, you can do cyclic permutations of this. So you bring the C out front, you have C dot A cross B, and then you have B dot C cross A. So that's something you can prove if you want to. That's just, you know, a lot of multiplications. This expression gives the volume of the object who's the parallelepiped that is spanned by these three vectors right there. Sort of a geometric proof of the equality here. Of course, you can also multiply those out. Good, this is where we'll stop. Next time, so I always like to put up what's going to happen next time, we're going to start talking about the differentiation and even integration of expressions using vectors. And we'll probably get into non-Cartesian coordinate systems as well. So next, differentiation. Which of course is going to bring us to the kinematics that we started with. Because we're interested in position, velocity, acceleration. So differentiation, kinematics, and other coordinate systems. Good. So I'd say everything that we've had on the last two lectures where I mentioned homework, that would be due this Friday, and then starting on that Friday lecture, they'll be for the following week. Okay, good. See you guys next time.